Hello everyone. Today we are sharing with you our work Improve Throughput for All or Nothing Multi-Commodity Flows with Arbitrary Demands. My name is Anya Chaturvedi and I am co-presenting today with Jamison. In our work, we consider the all or nothing multi-commodity flow problem. For an instance, we are given a directed connected edge capacitated network G with n vertices and m edges. We are also given k commodity sourcing pairs where a commodity I has the form SITI and has an associated demand DI and weight WI. For each commodity I, we seek to route either its entire demand DI or nothing at all, hence the all or nothing flow problem. To illustrate some essential definitions, we consider an example network. Here, we have two commodity pairs. Each edge is labeled with two numbers, where the flow on each edge is given in blue and the edge capacity is given in red. Notice that each commodity has an associated weight and demand, and we allow demands to be larger than the edge capacity. Here, we have highlighted the flow after routing commodity 1. One unit of flow exits S1 and arrives at T1. Likewise, we have highlighted the flow after routing commodity 2 and notice that the total demand has been split among multiple paths due to the capacity limits. This is something we permit. However, when we attempt to route both flows at once, we have no choice but to exceed the capacity on some edge, which results in an infeasible flow. And so in this example, we may only route at most one commodity. Since we can only route one of these commodities without an edge capacity violation, we choose the one with highest weight to maximize our throughput. With the ANF problem, we are tasked with finding a maximum weight routable subset of commodities subject to capacity and conservation constraints. As an example application, consider users requesting videos over the internet. Packets must be routed to each user upon request, but either all the packets for a video must route or none of them, so that the user does not end up receiving an incomplete file. Our major contributions in this paper are: we developed a deeper understanding of packing and compact edge flow ANF LP formulations and their equivalents. Our application of randomized rounding improves on performance over the state of the art by giving tighter theoretical guarantees, requiring less space and allowing for more constrained extensions. We also provide an experimental evaluation of our algorithms.
The ANF problem can be expressed as a packing formulation LP. Here, Fi is the set of all valid canonical DI flows for each commodity I. One can show that the size of these sets are exponential and finite. However, one can solve the relaxation in polynomial time using multiplicative weight updates. In this formulation, each commodity flow is expressed as a convex combination of flows in scripted Fi, and Xi indicates whether to route commodity I. The ANF problem is hard to approximate within a constant factor, but suppose we allow for bounded edge capacity violations, which we refer to as congestion. In the example from before, when we tried to route both commodities, the congestion exhibited here is 3/2, i.e. the ratio between the flow and capacity along this edge, and the largest one out of all of the edges. So even with a constant factor congestion, it turns out that this problem is still hard to approximate even within a polynomial factor. We use a bi-criteria optimization where we seek a feasible solution with at least alpha fraction of the optimal throughput and at most beta factor bound on the largest congestion. Our main theoretical contribution is given by this theorem, which demonstrates the existence of an efficient randomized algorithm that produces a 1 minus epsilon O log m over log m approximation with high probability. This improves over the state-of-the-art offered by Liu et al. We also consider the compact edge flow formulation. This is a standard flow formulation for ANF based on flow conservation. The formulation is polynomial in size, and we show an equivalence between this formulation and the packing formulation. That is, given a feasible solution to one relaxed LP, we obtain a feasible solution to the other relaxation of the same flow and objective values. Most importantly, our theoretical guarantees based on the packing formulation carry over to the compact edge formulation. One thing to note is we have this extra constraint here that strengthens the LP relaxation and allows for equivalence between or to the relaxed packing formulation. This formulation leads to a simpler randomized rounding framework and faster implementation in general. Our randomized rounding algorithm shown to the right is simple to implement and fast. And as mentioned before, the theoretical bounds based on the packing formulation still apply here. We even provide a de-randomized version of the randomized rounding algorithm that yields deterministic guarantees on approximation bounds. As an input to the randomized rounding algorithm, we require a solution to the relaxed LP. We explore 3 ways to do this, each providing their own pros and cons. Each one exhibits a trade-off between space and time, where Cplex is the fastest but the least space efficient. Multiplicative weight update is slow but space efficient, but permutation routing is faster than MWU, still space efficient, but it lacks the theoretical guarantees that MWU has. The choice of algorithm will be dependent on the network at hand. So bringing the whole algorithm together, you see that given an instance as input, we first compute the solution to the relaxed LP using one of these 3 algorithms. Then this solution is fed into either the randomized rounding or de-randomized algorithm, which then produces an integral solution at the end.
We perform many experiments on all possible combinations of algorithmic components on a variety of networks, but due to time constraints, we focus today on the Germany 50 network from SND Lab. This is a large network with a high number of commodities. For each experiment, we compute a throughput ratio based on the LP solution and also compute the largest capacity violation ratio. Note that since we allow capacity violations, throughput may exceed the optimal throughput. For these plots, the horizontal axis measures the throughput ratio alpha of each experiment, and the vertical axis measures the edge capacity violation ratio beta. On the left, we see the results of using Cplex to solve the relaxed LP. We gathered 10 data points for randomized rounding given in blue, and the result of the de-randomized algorithm is given in orange. The red star gives the ratios for the LP solutions for comparison. We see that the data points from randomized rounding are concentrated around a mean that is close to a throughput ratio of 1:1, and a capacity violation ratio of 2.5. Whereas the de-randomized algorithm achieves much higher throughput as it pushes the edge capacity violation factor up much higher, although that is still within the theoretical limit. This is primarily due to the greedy nature of the method of conditional expectations. The right plot shows the results of using MWU and permutation routing under various parameters. MWU and permutation routing solve the relaxed LP with an arbitrarily high precision given a parameter gamma. In comparison to Cplex, the MWU-based LP solvers produce much higher edge capacity violation ratios, but do not exhibit as large of a corresponding gain in throughput, likely because the solutions given for the LP relaxation are suboptimal. Again, when combined with the de-randomization algorithm, we see much higher throughput and edge capacity violation ratios that are much larger than the corresponding randomized rounding ratios. In general, we see that the ratios in all cases are well within our theoretical approximation bounds. For future work, we are interested in experimenting on large instances where due to space constraints, Cplex fails to solve the relaxed LP, and we therefore must rely on an MWU approach. We are also interested in conducting experiments for the packing formulation extensions. For example, we can further constrain our network by search for a feasible flow assignment of maximum weight, such that each commodity flow assignment uses at most 3 paths, etc. We are also interested in possibly improving the performance of randomized rounding using resampling techniques.
Thank you so much for watching.